Okay, hi guys. So I'm going to draw the resonance structure of OCN and then determine OCN minus and then determine which one of the structures is more stable. All right, so we first want to determine the total number of electrons, and we can do that by locating each element on the periodic table. Oxygen is in group 6, so it has 6 valence electrons. Carbon is in group 4, so it has 4 valence electrons, and nitrogen is in group 5, so it has 5 valence electrons. This -1 charge means that there's an extra electron present, so we add that one in as well. All together, we have 16 total valence electrons that we have to account for when we are doing our Lewis dot structure. All right, so so what do we know? Oxygen can make 2 bonds. Carbon can make 4 bonds. Nitrogen can make 3 bonds. Of the 3 atoms, we'll make carbon or central atom because carbon can make the most bonds. So we'll make carbon in the middle, and then oxygen can go to the left of it and nitrogen goes to the right. Now, if carbon is our central atom and it could make 4 bonds, then think about how we're going to be distributing our bonds. Maybe we can give a bond to carbon and oxygen and 3 bonds to carbon and nitrogen. That's okay. If you weren't thinking that, we could do another model. So maybe if you had carbon in the middle, oxygen to the left, and nitrogen to the right, and you decided you wanted to give 3 bonds to the oxygen and 1 bond to the nitrogen, that's completely fine too. What if you decided you wanted to split the number of bonds between the carbon, oxygen, and carbon, nitrogen? Carbon, double bond with the nitrogen, carbon, double bond with the oxygen. So each one of these structures, we arranged the number of electrons between the carbon and nitrogen and the carbon and the oxygen. Remember, I was thinking that carbon could make 4 bonds. I'm just thinking how I would distribute the bonds between these atoms here, stemming from that central carbon. Now we need to account for the 16 total electrons. Right now, we have 2, 4, 6, 8. We need to make sure that we get up to 16. Looking at nitrogen, nitrogen currently has 2, 4, 6, which means nitrogen only needs 2 more to get its octet. Carbon already has its octet, 2, 4, 6, 8. Oxygen has 2, 4, 6, 8. If we count all together, we should get 16. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. So everybody, each atom within this molecule has their octet. We could put brackets around it and put the charge, -1. Now if we look at this carbon, we see that carbon has 8, 2, 4, 6, 8. This nitrogen needs to have 8 as well. So we have 2, 4, 6, 8. This oxygen has 2, 4, 6, 8. All together, we need to check to see that it's 16. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. So we have 16 total electrons here as well. -1 charge. Let's look at this carbon, oxygen, carbon, nitrogen bond. Carbon has 8, 2, 4, 6, 8. Nitrogen has 2, 4, 6, 8. Oxygen has 2, 4, 6, 8. Altogether, we should have 16. 2, 4, 6, 8, 10, 12, 14, 16. So we have accounted for the total number of electrons in each one of these models. The fact that we used the same chemical formula and drew different representations of the molecule, we call these resonance structures. The only thing that is different about them is the placement of the double bond or the triple bond. Notice the arrangement of the atoms are the same. So you have oxygen and carbon and nitrogen, oxygen, carbon, nitrogen, oxygen, carbon, and nitrogen. If you wanted to do something like carbon, oxygen, and nitrogen, this would represent maybe an isomer. Okay, so these are resonance structures because the arrangement of the atoms within the molecule is consistent in all three representations. The only thing that is different is the placement of the double bond and the single bond and the triple bonds, etc. This is called an isomer because we have the same chemical formula, O, C, and N, but it does not have the same sequencing of the atoms. All right. If this was supposed to be an isomer, it should have resonance. It should have started with O and then C, then N. I hope that makes sense. Now, once we are able to draw out our Lewis dot structure, we need to figure out which one of these three models would be most stable. We do that by looking at our formal charges. So to calculate formal charge, we have this formula. We need valence electrons minus bonding, the number of bonds, and your dots. So sum up your dots, sum up your bonds, and then subtract it from the valence electrons. So let's look at this first example. In order to figure out which one of these molecules is most stable, we need to figure out the formal charge of each atom within the molecule. So we'd have to figure out the formal charge of the oxygen here, carbon here, and nitrogen here. And then we'd also have to figure out the formal charge here, here, and here for this other molecule. And same thing here. So let's start with the first model. To figure out the formal charge of the oxygen, notice that we have one bond. Oxygen has one bond, and it has 2, 4, 6 dots. So oxygen has one bond and 6 dots. So altogether, this is 7. And then the valence electrons that we got from the periodic table, we know that oxygen is in group 6, so it has 6 total valence electrons. So 6 minus 7 is -1. So the formal charge on the oxygen here is -1. If we do the one for carbon, carbon should always have a formal charge of 0 because it's a central atom and we accounted for all the bonds there. So let's look at the carbon. Carbon is in group 4, so its valence electrons is 4. Now, the number of bonds on this carbon is 1, 2, 3, 4 bonds. There were no dots on the carbon, so it's 4 plus 0. So that's 4 minus 4 is equal to 0. So the formal charge on the carbon is 0. Now let's look at the nitrogen. Nitrogen has 5 valence electrons, and the number of bonds here would be 1, 2, 3 bonds. 3 bonds and 2 dots. 3 bonds and 2 dots. So that's 5 minus 5, that's equal to 0. So the formal charge on the nitrogen is 0. Let's do the same thing for this model. We start off with the carbon. Not carbon. Let's start off with the oxygen. Oxygen has 6 valence electrons. We're subtracting that from the number of bonds and the dots. So this oxygen has 1, 2, 3 bonds and 2 dots. 3 bonds and 2 dots. So 6 minus 5 is equal to 1. So the formal charge on this oxygen is plus 1. If you do carbon, carbon should always be equal to 0. So carbon is equal to, there are 4 valence electrons on carbon. Then this carbon has 4 bonds, 1, 2, 3, 4. And there were no dots, so 4 plus 0. So again, 4 minus 4 is equal to 0. Carbon should always have a formal charge of 0 because that's the element that participates in the most bonding. Then look at the nitrogen. Nitrogen has 1 bond and 6 dots. So nitrogen has 1 bond and 6 dots. And nitrogen is in group 5, so it has 5 valence electrons. So it's 5 minus 7, which is equal to minus 2. So the formal charge on the nitrogen is minus 2. Now we need to do the same thing for this oxygen, carbon, and nitrogen. So with this oxygen, we need to think about the group number that it's in. So it's group number 6, so it has 6 valence electrons, minus the bonds and the dot. There are 2 bonds and 4 dots. So it's 6 minus 6 equals 0. Do the same thing for carbon, but we already know that carbon should have a formal charge of 0. And then nitrogen is in group 5, so it has 5 valence electrons. In this example, there are 1, 2 bonds and then 4 dots. So that's 5 minus 6 is equal to negative 1. So the formal charge of the nitrogen is a negative 1. Now, I just assigned formal charges on each one of these atoms within the OCN minus molecule or ion. We need to figure out which one of these is the most stable. To do that, we are looking for formal charges that are close to 0 as possible. And we also have to think about, are the formal charges assigned to the more electronegative atom? Okay, so if we were to look at, let's see, which one is the most stable? I would say it's definitely not this, because we have a +1, 0, and a -2. We want most of our formal charges to be close to 0 as possible. All right, so we would not choose this one because we have +1, -2, and 0. We're looking for mainly zeros. So one of these two structures is most stable. One of these two structures is more stable than the other. Which one is it? Well, we notice here that there's a -1 formal charge on the oxygen and a 0 formal charge on the nitrogen. Comparing these two, is oxygen more electronegative than nitrogen? Yes, it is. Oxygen is more to the right of the periodic table, so we would say that it makes sense that oxygen has a -1 charge. On here, we see we assigned a -1 charge to the nitrogen now and a 0 to the oxygen. We would not say that this is a more acceptable representation of the OCN minus ion because a -1 was assigned to nitrogen, and nitrogen is not more electronegative than the oxygen. So we would go with this first example here. This model is the most stable of all three. This one is the least stable. So the key takeaways are that Hold on, let me get my example notes. Okay, here it is. Structures that minimize formal charges or have negative formal charges is more electronegative. All right, so we're looking for structures that minimize or formal charges, key point 1, or have formal charges on more electronegative atom. So here we were comparing these two. The formal charge of -1 was on the more electronegative atom, which is oxygen, compared to nitrogen. So we can conclude that this is the most stable of all three. Again, we talked about isomers and we talked about formal charges, and I hope that resonated with you. If you have any questions, make sure you ask me them.